live presenters from your calculators. So like you don't have to like get up to the board or anything, but I'm gonna use this feature of the TI-Nspire software really quickly. So let's go to class, and is it under somewhere here? No. Here? No, come back. There is a way to do this. Live presented, there we go. So let's start with, I have no clue who this is.
Is it going to tell us who it is?
I can see who it is in just a second. Alright, so this is Grayson. Grayson, can you go back to your list and spreadsheets? Oh, you can't see that at all because it is... No, where did my mouse go there? Yeah, change the way it's projecting. It's extending instead of duplicating, which that might not mean it's on to you. Okay, so this is what Grayson and this whole group up here, I'm not going to just say it's Grayson, but here's Grayson's calculator. And so you'll notice some of us very quickly, I think Nathan quickest actually jumped right away or found the answer right away. At the very end of all this, Nathan, option 1 gave you how much money? $1,800,000. $60,000 a day. I would love $1,800,000. I'm not even going to front. Option 2, though, how much money did it give you? 10 million, 7, 3, 7, 418. I think there's some decimals in there too. So you tell me, which option are you going to go with?
Pennies.
Option 2, right? Those pennies. Do you think you were going to go with pennies from the beginning?
No.
No, I think I saw everyone writing down option 1 right away because, let's be real, $60,000 is a great deal of money. So this is why you have to collect full evidence, and learning how to write equations can be useful. I saw some people just typing in the days right away, and they were typing in how many days they got each time. Does that sound about right? Okay. Who was it? I know I saw somebody doing this originally. Gracie, did you have, not Gracie, Lexi, did you have your money in there? I know, I'm sorry. I don't know why. But you started typing your money in every time, right? And then we started talking about how you can do that more efficiently. So yeah, that was what I was asking you to do that, Grayson. So notice day 1, 60,000, and personally, I would even start with day 0. That might not make sense to y'all, but does anyone have an idea why I might start with day 0?
Because you have 1 penny.
Well, yes, and so we have $0 here and we have 1 penny here, but there's a bigger reason. Okay, let's say I were to go graph this information. That wouldn't just be 0, that'd be 0, 0, right here, roughly. And then the other one would be 0.01, 0, 0.1. Why might I want those 2 points? Why are those two points important rather than like this 1 and like 60,000 and the 1 and 0.02? Why do I want these 2 points?
Because they're on the y-axis.
They're on the y-axis. What are those called? Okay, I want you to flip your paper over really quickly, look at the back where it has whole class discussion notes, and I want you to go ahead and make this note right there that the y-intercepts are your best starting points for linear and exponential functions. This is not always true, but your y-intercepts are the best starting points for linear and exponential functions. These are the easiest to work with. There are ways to deal with it when you don't have the y-intercept, but the y-intercept is the best place to start. Okay? From there, I think most of us very quickly started to recognize patterns. All of mathematics is built off of patterns. If you can recognize patterns, you can be super successful. All right? So, what was the pattern under option 1? Plus 60,000 a day? plus 60,000 a day,
So
plus 60,000 a day, right? And so that never stopped, did it? Okay, what happened under option 2, Cameron? So we multiplied by 2, all right? And so we want to recognize, and we need to keep this in mind, I guess I really should put this over here so that I can erase that over there in a second. But we want to notice and keep this in mind that one of these types of functions is what type of function, or one of these functions is what type? What are the two types of functions? Linear and exponential, right? So one of these is linear, one of these is exponential, okay? So we see, and I also write this under the notes on the backside as well, tabular representations are revealing what? What do we see in the table?
A pattern.
The pattern, which that's telling me how it's growing, or there's a keyword that was in the objectives that starts with an R, or a phrase that starts with an R. The rate of change. Your tables are great for revealing the rate of change. Make sure you make that note. Tables are great for revealing the rate of change, which makes them useful for writing equations. The one before this? The y-intercepts are a great starting point. Just this one of the tables, tabular representations are great for rates of change. You need to be aware of that. Tables will make your life easier when it comes to rates of change. Okay? Now, does anyone have a guess though which mathematical representation would quickly show us which one is linear? Like we might already have a guess, but which one's going to show us what is linear? Which mathematical representation would show us which of these functions is linear? We've already looked at tables. So that is a graph, right? So let's create a graph. I think I already saw someone make a graph. It was people from group 4. So let's stop presenter from there. Let's go to Lexi. I know she had it. And so tools, go to your graph really quickly. Okay. Is that your exponential, or is that your option 1, or is that option 2?
2.
That's here, this one?
That's what it told me.
Mine is just
like that too.
Did y'all, hold on. There we go. That's what I was looking for.
There you go.
Okay.
Wait.
Her y-axis was messed up. Did you notice how it was e to the 8th? That's scientific notation for just multiplying by 10 to the 8th. So I want you to look at that, okay? Does that look like an exponential function to you? Or does that look like a linear function to you? No, that does not look linear whatsoever. So multiplying by 2, is that linear? No. So what makes something linear? Probably repeated addition. Quickly, Lexi, instead of the pennies, can you go to the option 1 really quickly? Notice this is the beauty of technology, is that you can quickly change out those variables and look at those different things. Man, look at that. What is that creating? A line. A beautiful line, right? Hey, Gracie, oh my gosh, why do I keep doing that? Lexi, can you go through and do the regression analysis and create a least squares regression line? Oh. Does anyone recognize that equation? Is that the equation some of us used? Yeah? I think most of us probably typed in 60,000, and we did times D or times days or whatever, but 60,000 just times X, right? So where is this plus 0 coming from?
It's just like straight on the line.
Okay, what is the equation of a line again? Y equals, what does B stand for? Oh, what was that point I told you earlier that you should probably always get? the y-intercept, which the y-intercept was? Oh. So the y-intercept is showing up right there in the equation, right? Okay. So here's a couple of notes. First off, I know it's a pain in the butt doing all that bivariate data stuff, but that's a pretty easy way to get that equation if you didn't recognize it on your own, correct? Okay. So, a couple of quick things I want you to notice and to make a note of right here. When we have a constant additive rate of change, what function are we looking at? That's a what? That's a line, so that function is linear, okay? So, a constant additive rates of change define what type of line, or what type of functions? Define linear functions. Constant additive rates of change define those linear functions. Those constant additive rates of change define linear functions. From there, I want to talk about a couple of details. Where do you see the constant additive rate of change show up in the equation? Does it? The slope. What do we mean by slope? That is the constant additive rate of change. So this slope, the slope is the constant additive rate of change. If you ever see me write ROC, what do you think I mean? Rate of change. Okay, so I'll write ROC for rate of change. Okay, but it's a constant additive rate of change.
Can I get my equation for pennies? Or what do they say? No.
No, we're not going to say we're going to talk about it in just a second. So the slope is the constant additive rate of change. M is multiplied by x because y.
Are you saying y or are you asking?
I'm asking you all y, right? Y is m being multiplied by x. Say it one more time. Okay, I think someone said it there, I couldn't hear it, but DJ's pointing it out, and this is what we need to recognize. That multiplication is repeated addition. This is the y behind this equation. M is multiplied by x because the slope is repeatedly added. It's all about patterns. Okay? M is multiplied by x because the slope is repeatedly added. We need to recognize that detail. Because when you can find that constant additive rate of change, it makes it easier to write that equation. Do we have any questions up to this point? Huh? Not yet? Nope. Still taking some notes. Okay. Also, where m is the rate of change, what is b? The y-intercept, or a really good what? Is the first note we took. This is the y-intercept.
Starting point.
It's a great starting point. You need to know what the different parts of that equation mean. Those pieces of that equation show up again within exponential functions just a little bit differently because of how an exponential function works. Does that make sense? Okay. So that is the y-intercept is a great starting point. Lexi, can you go back to your listen spreadsheets really quickly? Just listen spreadsheets, yeah. Okay. So can you click on your equation that you wrote for pennies? So we can all see it. So pennies, right? So pennies, and really, I will say it's not necessarily pennies. We started with pennies, but obviously got way more. 0.01 times 2 raised to the number of days. Okay? Can someone who came up with this equation in a different group talk us through where that equation comes from? Yeah, you would get in the amount of money for that one. But I mean, like, when I look right here, where's this 0.01 coming from? Where is this 2 coming from? Why is there an exponent of d? On day 0, wait a second, that's the what then? If it's on day 0?
Y-intercept.
Oh, that's the y-intercept. But just like we had a y-intercept here, right? Except we're adding in this case, and here we are repeatedly multiplying. Okay, so that's my y-intercept. Again, a great starting point, right? So where is this times 2 coming from? Because you're multiplying? I think, so Shannon, what did you say your wording was that we were what each day? Started with a D. You don't remember what you said? I think you originally said we were doubling, right? Multiplying by 2, doubling every day, right? So that is my what type of rate of change? It is constant, but is that additive? Because what do we mean by constant? You're repeatedly doing it the same every single time, right? But that's not constant additive, that's constant multiplicative, right? That is the, yeah, that's a word, constant multiplicative rate of change. This is also known as a common ratio. You need to highlight or underline that word because that's one of the big ideas. Right, so that sheet that I gave you big ideas on, common ratio is on there. Okay? Of a what type of function? Of an exponential function. So what type of rate of change does an exponential function have? What type of rate of change does an exponential? Multiplicative. Not just multiplicative, a constant multiplicative, right? That common ratio is in there. Yes, ma'am.
So is the formula changing?
What do you mean?
But like on that problem you got your y-intercept at the end. On that problem you got your y-intercept
At the beginning?
Yeah.
So technically you can put it in the end. Really, actually, we're still on Lexi's, right? Can you hit menu for me really quickly, Lexi? And go to statistics again. And then stat calculations. And stop right there. I want you to look at this. Do you see this option for linear regression where it's a plus bx instead of mx plus b? So the traditional exponential function is a times b to the x. And this is why my favorite linear equation is a plus bx. Notice those are the y-intercepts, right? And there's my rate of change. So it depends on the way you write it, okay? I went with this because I knew that y'all were used to y equals mx plus b, but like that's actually my preferred method. If you look up there when I wrote it last year, maybe I didn't write it that way, but that is my preferred method, is that a plus bx. It's the same thing and it makes more sense to me because really what are you doing? You're really starting at $0, right? My y-intercept, and then you're adding $60,000 every day. That's why I like the a plus bx version. Yeah. Okay. So it's not really, it's just you can flip the order. It doesn't matter. Okay, and then so here's a huge thing to notice. We've already said it's an exponential function. Why is it called an exponential function? Because there's an exponent showing repeated what? Multiplication, right? And so please notice how I'm taking this equation, I'm breaking it down so that you can understand where every part is coming from. That way you can apply it on your own. You need to make sure you have notes on where this equation is coming from and how it works so that you can do it on your own. This exponent, ooh, I just realized that probably isn't in the frame for the camera, but I've talked through it. Hopefully it'll work. So this is the exponent because why? Because we are what? Or this function is repeatedly what? Because the function is repeatedly multiplying. Okay, that is our summary of linear and exponential functions. We're going to look at a couple more things in a second. Okay, you need to have those notes down. Racing you awake, buddy? All right. Lexi, can you go back to 1.5 really quickly? And go to pennies for the y-axis, the y variable. All right. I want you to notice, does it make sense to use a linear regression in that case? No. Okay. So click on the line and delete it.
Delete.
Just hit the backspace once you highlight the line. Okay. Now do a regression analysis again though. So hit menu, analyze. Let's do a regression. It may not do exactly what I want, but we'll see. Go to show exponential. Ah, it did. Notice that calculator was able to create a perfect model. You see how this curve goes perfectly through every single one of those points?
Yes.
So is this a powerful skill to help us figure out what the equation is so that we can then explain the equation? Yes. Right? We knew the first option was linear because it had what type of rate of change? Constant additive rate of change, right? By the way, what's that constant additive rate of change called?
Common word. The slope.
The constant additive, I heard someone just say it. The slope. Remember, if we're looking at a line with a constant additive, that's the slope. Please note, this is also called a common difference because that also shows up under your big ideas. Okay? So, it's a common ratio for exponential, it's a common difference for linear, right? The slope is what you've always seen in the equation, but we can also find that through a common difference. That's a huge thing to notice. And again, it's on your big idea sheet. So I will point out, up to this point, if you look at your big idea sheet, we have covered linear function, we've covered exponential functions, we've covered mathematical representations, and common differences and ratios. That's a lot of those big ideas within this one lesson. We need to make sure that we know those things.
You said, what about the,
I'm confused.
what you said?
What do you mean?
You said the common difference.
The common difference is the slope. It's just another word for the slope.
So when you say common ratio, what would I put there? Constant.
The common ratio is the constant multiplicative rate of change. Really quickly, to show you why it's called a common ratio, if I were to take 0.08 and I create a ratio with the previous value, what number would I get? That's why it's called a common ratio, because if I take the current value and I do a ratio with the previous, I get that multiplicative rate of change. This is called a common difference, because if I take 60,000, the current, and I subtract the previous, what do I get? 60,000, right? So notice that is a common difference every time, whereas the other one's a ratio. I was just going to give you those names, but that's why those are the names that they are. Okay? Do we feel like we have some understanding of a linear function?
Yes.
On a graph, what does a linear function look like? A line, right? What makes a linear function linear? What? That constant additive rate of change, right? Just to work on that language a little bit. That constant additive rate of change is called a, what's the name of that constant additive rate of change? Slope or common difference. You gotta know those vocabulary terms. If you're gonna talk about the mathematics, you gotta know how to talk about it, use the terms correctly.
So the slope is known as constant common difference.
So slope and common difference are the same thing, and that is the constant additive rate of change of a line. Okay? And so what is an exponential function going to look like on a graph?
A line.
Is that a line?
A curve.
It's going to have, and it's literally called an exponential curve. There's no other way to describe it, but it's called an exponential curve. Okay? There's a few different versions of it, but that is, but it's always going to curve like that. And what makes an exponential function exponential? Repeated multiplication, called a common ratio. Okay? The multiplicative rate of change is called the common ratio. Okay. We good up to this point? Any questions? Okay. By the way, and this doesn't really impact a lot, but I will point this out. Why do you think we ended up going with option 2?
Because they made more money.
Okay, obviously, but why did it start to make more money?
Because the number was getting.
It was multiplying. Even though it started out with a penny versus $60,000, if you keep multiplying, what's it eventually going to do? It's going to get bigger, as long as that number is greater than 1, right? So I do want you to notice if you're constantly multiplying, it will eventually outgrow it. It didn't actually outgrow it until like day 27 or so. Because if you think about it, 10 million at the end of day 30 means about 5 million at the end of day 29, 2.5 million at the end of day 28, 1.25 million at the end of day 27. So at the end of day 26, it was like 600,000. And that would have been way less than what you had under that constant additive rate of change. But eventually, once it started catching up, it caught up quick. And that's that curve that we saw here, right? See how it just started to jump because of that multiplication. Alright, we good? Okay. This part I'm not going to cover because this was actually designed to just be an extra thing if people got done with 1 and 2 early. I will make the note here, in this problem, you would actually choose this third option over the multiplicative or the exponential function. I specifically designed it so that this gave you a little bit more money, but if you actually went 1 more day, you would go with the exponential, because eventually that exponential, that multiplicative rate of change is going to outgrow it. Does that make sense? Okay, so that's all I was doing there. By the way, when I look up here, what is the y-intercept of this equation? Go ahead and look at number 3 and write this note down, but what would be the y-intercept? $2 million, right? Which means, before you even work a single day, how much are you making? $2 million. What is the constant additive rate of change for number 3? 315,000. Man, if I can make $2 million for just a signing bonus, and then $315,000 every single day, I would love that. But, again, eventually option 2 would be better, just not within day 30. Does that make sense? Okay. And so, if I were to make a table out of this, what would I see happening on the right-hand side? Huh? It's going to increase how? Multiplying, adding, subtracting? I would say it's multiplication, so it'd be repeatedly adding by 315,000. And then, if it was a graph, what would we see? A line. We all get on those details. Starting to make some sense? Feel comfortable with that? Kyle's giving me eyes like, no, Mr. Kinney. You good?
Yeah.
Okay. So the homework, the green sheet that I gave you, you should be able to do all of that homework off of what we have done so far, because what type of functions are there? Huh? It's either linear or it's exponential, right? So look at the, I'm going to have to resend the directions out because that's not what the direction is supposed to be. I will email you directions during the second block for this, just by sending out what the actual file is supposed to be. Apparently I didn't save it correctly, so I didn't print out the right sheet. But there are different directions for this one. Just look for that email this weekend, okay? Basically what it says is, don't do 21. So go ahead and mark out 21. And then it says to find the rate of change and write the equation. Or identify what type of function it is, the rate of change, and write the equation. Okay? So now we are moving on to the gold rush task. Okay? I've already told you, you may not remember this, but I already told you, this unit is mostly on what type of function?
Quadratic.
Quadratic. It's up here already, right? So, in order to understand quadratic functions, yes sir. Someone's got an extra one here, then. An extra gold rush task. You should have a second white sheet. There it is. I'll say, I know I put 4 out. Okay, so in order to properly understand quadratic functions, you have to be able to contrast that with linear and exponential. Linear and exponential come first, then quadratics. So, what is the first thing we're trying to learn about quadratic functions? The what change? The rate of change. Does it say constant here? No.
No.
Okay, let me go ahead and tell you. The only types of functions that have constant rates of change are linear and exponential. That rate of change is going to change, and we're going to explore what that actually means. We need to understand how quadratic functions appear in tabular, graphical, and algebraic representations. By the way, which of those representations do you think we're going to find the rate of change? Tabular, right? That doesn't change. The tables help us find our rates of change. We good on that idea? Okay? And then we're going to begin writing explicit quadratic equations. That may seem like a weird detail, that word explicit. These are all explicit equations where you have an input and an output. There's also a type of equation called a recursive equation that we're not going into. We're just doing explicit to save us a little bit of time, okay? So here's the context for gold rush. In the 19th century, many prospectors traveled across North America to search for gold. A man named Dan Jackson owned some land where gold had been found. P.S. Life tip. Own land, don't rent. Okay? If you can get to a point where you can own a house, own land, you are going to pour money into yourself instead of giving someone else money, okay? And sometimes you can rent that land out to other people. So instead of digging for the gold himself, he rented plots of land to the prospectors. Dan gave each prospector 4 wooden stakes and a rope measuring exactly 100 meters. So when they set it up, okay, they're going to have to set up a rectangular plot of land